Awesome. Thank you. So actually, I want to write this back the way we had it. I want to write the integral from 1 to infinity of e to the negative x dx, and we want to find that integral. So two things that we need to do, but what kind of integral is that? What's it called?
Indefinite.
It's a improper definite integral.
Okay, yeah.
So it's improper because of one of the endpoints is either undefined or infinite, and it's infinite. So we're gonna start by writing this as the limit. And let's just use t, because why not? The limit is t goes to infinity of the integral from 1 to t of e to the negative x dx. And there's one other little thing that we want to do. And what is that?
X dx. And then we take the limit of
I'm going to erase this, the part of the board that's to the right.
Okay. Let me just take a quick.
Sure.
So why is it being? Oh, it's on the other side today. It's like, oh, I guess I flipped it different.
So we have the integral from 1 to infinity of e to the negative x dx. We said that was the limit as t goes to infinity of the integral from 1 to t of e to the negative x dx. And what do we need to do to determine what that integral is? Can we just take the integral without any work?
Yeah, would it be negative e to the negative x?
Yes, but why the negative? Let's do the step that shows why it's negative. Yes. So let's just do a quick u substitution. We're gonna let u be negative x. So the du is
Negative 1.
good. And we can multiply both sides of this by -1 so that we have positive dx on the right and negative du on the left. And there's one other little thing. We want to change our limits of integration. Let's see. When x is equal to 1, what is u? Good. When x is equal to t, what is u? Good. So we've got the limit as t goes to infinity, the integral from -1 to negative t of e to the u, and then we have a negative du. And that negative multiplied by the du, what can we do with it?
Take it out.
Good. So let's come here. We've got negative limit as t goes to infinity, -1 to negative t e to the u du. And that is, the integral of e to the u du is just e to the u. So we have negative limit as t goes to infinity of e to the u evaluated between -1 and negative t. So let's put the upper value in and the lower value. And now let's write them without the negative exponents.
Wait.
So how can I write e to the negative t without that negative exponent? Good. And e to the negative what? Good. And what happens to 1 over e to the t as t blows up? Good. So we have negative 0 minus 1 over e, and we get one over e. Since the integral converged to a value, we don't know if the value is the same, but all we know is that therefore our original series will also converge. So since the integral from 1 to infinity e to the negative x dx converged, then the related series also converges.
This is gonna be equals negative. So this is the, so 1 over e was that final answer.
Yes.
And then since it goes to an answer,
That's
it
right.
converges.
Then it
Okay.
converges, and since it converges, and we have continuity on 1 to infinity, and we have a decreasing positive function, then the series will also converge.
Gotcha. So e x. The series of and it's 1 and also converges. Let's go take over. Quick snap right now.
And now we want to look at a related series. So, can we compare the series n goes from 1 to infinity of e to the negative n with this series? N equals 1 to infinity, e to the negative n So can we compare those?
So this is kind of like example 8 star.
Yeah,
Okay.
it's the 8 that I intended to do. But yes, 8 star is lovely. And since the series n goes from 1 to infinity of e to the negative n converged, we can only compare these two series if the second series is smaller. So the answer is only if the second series smaller or equal to the one that we know converges. So if you have something that converges and you find something that is smaller or equal, then we'll know that the second thing also converges. Well, let's see, what's going on in the denominator of this second series? It's, the denominator's getting bigger. So if I just look at those two terms, and we're assuming here that n is bigger than 1, what direction of the inequality would I write? Which one is larger, e to the negative n or e to the negative n divided by n? That's right. Good. And that's because we're starting with n equals 2, 3, 4. As long as I'm adding something positive and bigger than 1 to the denominator, I'm getting smaller. How would we compare then e to the negative n divided by n plus cosine squared of n? So can we continue the same direction of inequality? We have one good thing, we're adding. So adding is usually making something bigger.
Smaller.
Well, in overall smaller, but the denominator bigger. And what about n, the cosine squared of n? Is that always positive or 0? That's right. It's always positive or 0, so we can put that we're getting smaller or staying the same. So since cosine squared of n is between 0 and 1, then adding something is going to make the denominator itself bigger. And it doesn't matter that this thing we're adding is less than 1, because we've already got something bigger than 1. So we're definitely increasing the size of the denominator and therefore decreasing the overall size. So can we compare those two series?
Yes.
Yes. So, yes. And we don't know what it converges to, but we do know that the series n equals 1 to infinity, e to the negative n over n plus cosine squared n converges. What if we had had a minus sign between the n and the cosine squared n?
We wouldn't be able to do it because it would become -1.
Right, we could have been subtracting. We would have been subtracting something. So it only worked because we had plus sign. Could I have subtracted something from the numerator? Would that have been okay?
Yes, because that's not, what we're looking for is the denominator going towards 0,
That's right.
essentially.
Or going toward infinity?
Going toward infinity.
Yes,
Yes,
exactly
correct,
right. Okay, good.
Is there any example in which, say, you would have a subtraction that would equal out? So maybe say, I suppose if you'd had like a negative n minus a cosine something something, potentially it
it would still converge?
Okay.
Yes, yes, so all we could say, if we had had this series that we were comparing to, so if we compared with u negative n over n minus cosine squared, is that we couldn't use the comparison test.
Okay.
We'd have to use a different test.
Test. But that
So
would be
this
something that
probably does converge still, but not, we can't prove it using the comparison test.
Gotcha. Okay.
Okay. Oh. Groovy. Okay, example 9.
Okay.
Can I erase this?
I'll just pan back over to it right quick and take a quick snap and we shall be good to go.
Okay. Awesome. So let's look at the series n equals 1 to infinity n squared plus 2 over n to the 4th plus 5. And we're thinking about comparing. So what could I get rid of in this fraction so that I would have a correct inequality symbol here? N equals 1 to infinity up. Can I get rid of the plus 2 in the
Yeah.
numerator?
Yes.
And have it get bigger?
No.
That's right, so we have to leave that plus 2. What about the plus 5 in the denominator? We can get rid of that, good. Okay. Well, now this looks like something that we can evaluate using a different rule. So let's see what is the limit as n gets huge of those terms, n squared plus 2 over n to the 4th. Because we have to have that limit going to 0. Okay, well, if we just plugged in infinity, what would we have in the numerator here?
Infinity.
And the denominator? And that means we can use which test?
L'Hopital.
L'Hopital's rule, good. Which says that this limit will stay the same if I take derivatives of numerator and denominator. And what's the derivative with respect to n of the numerator?
2n,
Excellent, and the denominator?
4n to the 3rd.
And can we simplify this before we do anything?
Yeah, 1 over 2.
Okay, good. And what does that limit, what is the value of that limit?
0.
Okay, yay. So we know that it's looking good for our original series to converge, but what are we gonna use? So let's look at this integral. Consider the integral from 1 to infinity of x squared plus 2 over x to the 4th dx. And that might look horrible until we remember that we can write this, we have one denominator and 2 numerators. We can write that as the sum of 2 fractions. We can write it as x squared over x to the 4th plus 2 over x to the 4th. And that looks like something we can handle. So let's see, we've got this first one. What do I need to do before I even write that integral symbol again?
Take the limit.
Good. So we've got the limit as t goes to infinity of the integral from 1 to t. And let's reduce that first fraction.
So just,
Good. And can we write both of those fractions so that they're not looking like fractions?
x to the -2, and then 2x to the -4.
Excellent. So we have x to the -2 plus 2x to the -4 dx. And do we know how to find those integrals?
Yes, power.
Let's see, what do we do with the
Plus
the next
1.
one? We add, and
So
then
that
we
would
divide
be-
by that. So -1 plus 1 is,
-1.
and we're dividing by,
-1.
good.
Sure.
And we're doing what to the -4?
Uh,
So we get 2x to the -3 divided by, okay, good. And we're evaluating this between 1 and t. Okay, now let's make those look like fractions again. So we have the limit as t goes to infinity. How can I rewrite x to the -1 divided by -1?
x and 1 divided by 1.
-1 over x.
Good. And then I'm gonna pull out this 1/3, but it's a -1/3. And I've got a 2 still in the numerator. What happens to the x to the -3?
Goes to the denominator.
Good. All right. Now it makes sense to put in our limits of integration. So we've got -1 over t minus 2 over 3t cubed minus -1 over 1 minus 2 over 3 times. Is that right?
Some, yeah,
Upper limit,
lower limit.
lower limit, okay.
Okay. And then we
And both of the t's are in denominators, so what is gonna happen to that entire first term
goes to,
as t goes, yes. Good, so this whole thing is going to 0, and let's see what we've got left. negative times a negative, both things inside are gonna be positive. So I've got 1 plus 2/3 and 1. Can I write that as something over 3? Let me rewrite this just one time. I've got
Over 3.
1 over 1 times what? Plus 2 over 3. And yes, we can multiply the 1 by 3 over 3. That gives us 3 plus 2 over 3, and that's 5/3. So what does that say about our integral? Does the value of the integral matter right now? That's right. But what does it say about this integral? It converges, it has a value. So since the integral from 1 to infinity of x squared plus 2 over x to the 4th dx equals 5/3, then this thing we were comparing, this series, n equals 1 to infinity of n squared plus 2 over n to the 4th, also converges. And what else can we say, therefore? So the series here converges because this integral converged. And what was the original series we were looking at? That's right. So our original series will also converge. That's right, because we're smaller than something that converges, so we will also converge. Okay.
So, the whole making seeing if the limit is 0, that's just the divergence test?
So that's just the divergence test, yes. That tells us whether or not we even want to bother.
Okay.
So if we had not gotten 0 when we took the limit of the terms, we're done, it diverges. Okay, the next test that we're going to look at is called the limit comparison test.
And this,
And it says, if we have A sub n and B sub n are non-negative, which just means that the A sub n's are all greater than or equal to 0, and the B sub n's are also all greater than or equal to 0 for all n. Then we're going to consider the limit as n goes to infinity of B sub n over A sub n let's just call it a number, let's say that it equals C. If C is positive and less than infinity, then what B sub n does, A sub n will do. And if B sub n diverges, also B sub n will diverge. Okay, well, let's play with it. Let's see, let's consider the series n equals 0 to infinity, 1 over 3 raised to the n minus n. So what we're gonna do is compare the above series with n equals 0 to infinity of just 1 over 3 to the n. So we want to find, do you see that we can't use the straight up limit, pardon me, the straight up comparison test here? Because just because 1 over 3 to the n converges, if I'm making this thing smaller, we don't know what's going on with it. Right, I'm decreasing the denominator, so I'm making all the terms bigger, so we don't know what's going on with this other series, but we could see what's going on with this limit. So let's look at the limit as n goes to infinity. Hey, Robert. Of 1 over 3 to the n divided by 1 over 3 to the n minus n. So we're letting this first series be our a sub n's, and the second our b sub n's.
This is
And since we've got a fraction in the denominator, can we just invert and multiply?
yes.
Okay, good. So this is the same as the limit as n goes to infinity of 3 to the n minus n divided by 3 to the n. And this is nice because we can write this as two fractions. This is equal to the limit as n goes to infinity, 3 to the n divided by 3 to the n minus n divided by 3 to the n. Well, the first value is just going to be
1.
1. So we've got the limit as n goes to infinity of 1 minus n divided by 3 to the n. If we just let n go to infinity, what would we have in the second fraction?
So if we let n go to infinity, it's infinity over a bigger infinity.
That's
so-
right, but still infinity over
Infinity.
infinity. So we can use L'Hopital's rule. And we'll have the limit. N goes to infinity. 1 minus the derivative of the top. Good. And the derivative of the bottom is gonna be natural log of 3 times 3 to the n, is that right? And what does that second fraction go to as n goes to infinity? That's right. So this equals 1 minus 0, which is 1. And we said over there, if we get a positive answer, and it's not infinite, then the behavior of the top series controls the behavior of the bottom series. Well, what do we know about the series 1 over 3 to the n? I wonder, let's look at that. Let's look at n equals 0 to infinity, 1 over 3 to the n. Bless you.
Thank you.
Is that 1 the same as 1 to the n? Is 1 to any power still just 1?
Mhm.
Yes.
Yeah, so I could write that as 1 to the n over 3 to the n. But now I have the same exponent, so I can bring it out. And I've got 1/3 raised to the n. And what kind of series is that? If I have a number raised to a power,
Is that geometry?
that's exactly right. So this is geometric. And here, what is r? What is the number being raised to the power?
One-third.
1/3. And we said that a geometric series converges if that r in absolute value is less than 1. So we're good. And that means that this first series we looked at
Mhm.
converges, and what does that say about the second series? So the series in the numerator converged. And what does that say about the series in the denominator?
It also converges.
It also converges, good. So we know that this series, 1 over 3 to the n minus n, as n goes from 0 to 1, converges.
So since the geometric converges, and we can compare the geometric to our
Yeah, and since
original,
we put the geometric one that we know about in the numerator,
yeah.
and the overall thing came out to a value
Mhm.
that was positive and less than infinity, then the behavior of the top controls the behavior of the bottom.
So top controls bottom. Controls bottom, and they converge.
Okay, that was example 10. I neglected to number that. Let me know when you're ready.
Okay. Let me take a snapperino, and we shall be.
Alrighty. In example 11, we're trying to make a decision about the series as n runs from 2 to infinity of 4n squared plus n divided by the cube root of n to the 7th plus n cubed. That is the cube root, right?
5,
I think so.
6, that. Yes, it is 4n squared plus n, the cubed root of n to the 7th plus n cubed.
And the first thing that we're gonna do is just a little bit of algebra in the denominator. So let's just notice that if we have the cube root of n to the 7th plus n cubed, well, there's a common factor of n cubed in those two terms, yes? So I can factor that out. What's left? Good. And this is nice because we've got a perfect cube. Cube root of n cubed is,
Because it goes n to the 1/3 times 3.
that's right.
Yeah, and then n to the 4. So it'd be 4/3, yeah? Plus 1. Or are you just leaving the cubed root? Okay.
Yeah, I'm leaving the second part in the, under the root, but I've got an n that comes out. And that'll be nice for us. Because now, we've got 4n squared plus n. Do I have a common denominator, a common factor in the numerator? Okay, let's factor that out. And I am gonna go ahead and write the denominator as the 1/3 exponent.
And you just went ahead and changed the 4n squared plus n to n.
Oh, thank you. Yes,
Didn't you pull out n cubed?
in the denominator?
Yeah.
Yes. And we've got a cube root. The cube root of n cubed is n.
Oh.
And that's the only reason we would even bother factoring out something common, because we can actually simplify it.
So 4n.
And now we've got a common factor in numerator and denominator. And we check up here, we're not starting at n equals 0. So we're completely allowed to divide out common factors. So now we're only considering the series 2 to infinity of 4n plus 1 over n plus 1 to the 1/3.
So, two.
That one's N4.
Say again?
That one's N4.
Oh, thank you, into the 4th. Yes, thank you. I was just testing you, Soma. Not really. So, what do you think we should compare this series with? Let's start with some inequalities. Say again? Yes? So how can we make this thing bigger? Do we increase the numerator, increase the denominator, or decrease the numerator, or decrease the denominator? We want to go bigger.
Decrease the denominator.
Decrease the denominator, good. So let's get rid of that 1. And now we've got n to the 4th to the 1/3. Well, that's the same as n to the 4/3. And in the numerator, 4n plus 1. We can do a little bit more algebra. We can rewrite that. So n goes from 2 to infinity. I'm just gonna write it as 2 fractions, because I've got 1 denominator now. And let's write the denominator as n to the 4/3. The first numerator will be 4n. The second numerator will be 1. And we can do a tiny bit more algebra on that first fraction. Let's just do it over here. What's the exponent on n if no exponent is written?
1.
So is this equal to n to the 1 minus 4/3?
Yes.
Yeah, just using rules of exponents. And 1, that's 3 over 3. So this is 3 over 3 minus 1 over 3 minus 4 over 3. And that is good. Okay, good. And I'm gonna drop it back into the denominator. So we have n from 2 to infinity of 4 over n to the 1/3 plus 1 over n to the 4/3. And what do you think would be good to compare this with? Just look at the first one. What's good to compare 4 over n to the 1/3 with? let B be. What if we just let B be 1 over n to the 1/3? For this first fraction. So we're looking at the limit as n gets infinite. We want n, b to the n on top, so 1 over n to the 1/3, and a sub n on the bottom, the one we're comparing with. When we invert the denominator fraction and multiply, let's just write it out. Then we'll have the limit as n goes to infinity. Here's this first n to the 1/3. And then I'm finding the reciprocal of the denominators. That'll be n to the 1/3 over 4. And what is nice? Yes. This limit exists and equals something positive. Pardon? Well, we don't, for the limit comparison test, we just want positive, not infinite. So now let's look at this second bit. What do you want to compare 1 over n to the 4/3? Well, we don't even need to do that, but let's look at the integral test for this one. So if we have the integral from 2 to infinity of 1 over x to the 4/3, we could rewrite that. The limit as t goes to infinity, 2 to t. Can I write x, 1 over x to the 4/3 as x to the negative 4/3? And then we can just use the power rule for integrals. So it's our new exponent. Negative 4/3 plus 1. Good. And we're dividing by negative 1/3. So let's multiply by negative 3. And that negative 3, we're gonna pull out. So I've got negative 3 x, instead of x to the negative 1/3, I'm gonna write x to the 1 over x to the 1/3. And I'm letting 1/3 go, I mean the 1/3 t, wait, 1/3, x to the 1/3, I don't even know what I'm saying. So we're going x equals 2 up to t. At t, we'll have 1 over t to the 1/3. At 2, we'll have 1 over 2 to the 1/3. And whatever that value is, as t goes to infinity, do we get a value? Yes. So almost 0. We get negative 3 times negative 1 over cube root of 2. So we get that this integral exists and equals positive 3 over 2 to the 1/3. And since it has a value, what can we say about the original series? Since the integral has a value,
It converges.
it converges, good. So we've got both parts, we've shown that both parts of this series converge, so what can we say about overall? It overall converges, good.
The like an n to 2 to the e to infinity, that's a series, right? I just wanted,
Yes.
Okay, I just wanted to use correct terms. So since series. And since.
What time are we having?
It is 12:09.
Oh, okay, we can finish this chapter. Okay.
So since this.
Oh, let me know when you're ready for me to erase.
Okay, yeah, let me just.
Because we're gonna do the alternating series test next.
Make sure I can read all that. Yep, okay. Should be good to go.
So if we have a series a sub n, and a sub n is equal to either -1 to the n b sub n, or a sub n is equal to -1 to the n plus 1 b sub n,
And this is alternating series test you said.
then if the series b sub n converges, where we're assuming that these b sub n's are all positive or 0, then the series a sub n converges.
So. So alternating series versus.
Okay, so let's look at example 12. Let's consider the series. N runs from 1 to infinity, -1 raised to the n minus 1 divided by and we want to compare this with one of these models. So can we write either -1 to the n minus 1 over n equals -1 to the n b sub n, or should we rather write -1 to the n minus 1 over n equals -1 to the n plus 1 b sub n? Are either of those a good match? Which one?
Plus one.
The plus one, good. And that's because we're looking at, if n is even, the exponent is odd. If n is odd, the exponent is even, and the same is true for n plus one. Can we do any little bit of algebra to see what we should let b sub n be?
You can divide it. Get B sub n by itself.
Okay, yeah, let's see what happens if we do that. So we've got -1 to the n minus 1 divided by n. And since I've got a fraction already happening, can I multiply by the reciprocal of -1 to the n plus 1? Can I multiply both sides by the reciprocal of -1 to the n plus 1?
Yeah.
Good. Good. And let's do just a tiny bit more algebra. We've got -1 and -1 to the n plus 1. I've got n minus 1. And I want to do something so that I get matching terms, numerator and denominator. What can I add to -1 in order to get +1?
1 or 2.
2. If I add 2, I need to subtract 2. And now this first bit is what we wanted. N plus 1, and we also have times -1 to the -2. Still all over n. But what can we do very nicely now? Do we have a common factor in numerator and denominator? Yeah. -1 to the n plus 1 exactly matches -1 to the n plus 1. So we can divide those out. And all we have to do to find b sub n is mess around with this a little bit. What is, how should I rewrite -1 raised to the -2? Right now I've got -1 raised to the -2, and it's all divided by n. How can I make the negative exponent go away?
Put in the denominator.
Good. So this is the same as 1 over -1 to the +2 times n. And now we have an actual number. What is -1 squared?
1.
1.
So 1 over 1. Which is
So
gonna
we
be
want
1
b
over
sub
n.
n to be 1 over n. And let's see what it says, what needs to happen. So we needed two things. We need the limit as n goes to infinity of the b sub n's to be 0, and we need the sequence b sub n to be decreasing. And are we good in both? Definitely, as n goes to infinity, 1 over n is gonna go to 0. And if I increase denominators, am I decreasing the terms? Yeah, so we've got checks on both of these, so therefore, our original weird-looking series converges. And the cool thing about this is that we're not saying that the series of B sub n converges. We're saying that these B sub n's that we're comparing with, the limit goes to 0 and it's a decreasing sequence, but that makes the alternating series converge.
Therefore, n plus 1, n minus 1.
Let me know when you're good for me to erase.
Yeah, I didn't pan over, so I'm gonna leave that for a second.
Sure, no rush.
Random form.
Oh, it's earlier than I thought. But actually, I think I wanna stop here. I want you to do a short quiz, and you can go ahead and stop the recording.
Okay.